Hello and welcome. Today we delve into a dark chapter of aerial warfare, where cutting-edge technology and deadly innovation collided over war-torn Western Germany. A single moment on February the 11th, 1945, would forever change the understanding of high-speed combat and aircraft control. Imagine a fighter pilot, locked in a deadly dance at 400 miles per hour, fighting to control an aircraft whose ailerons have become almost completely frozen. Could a seemingly simple device, the spring tab, really turn the tide of battle? How did British engineers craft a system that defied the very laws of aerodynamics, allowing their fighters to outperform German planes in both agility and survivability? Why did so many Luftwaffe pilots lose their lives in encounters with these seemingly invincible machines? And what secret revolution in aircraft design was secretly transforming the skies, leaving the German fighters helpless and unmanageable? All of these shocking snippets are pieces of a larger puzzle. How a revolutionary control system called the spring tab turned high-speed dogfights into a brutal game of survival, and why Germany's most advanced fighters struggled to keep up. In this video, we will uncover the origins, mechanics, and devastating impact of this technology, separating myth from fact and revealing a hidden war behind the war. The story begins with a daring innovation that changed aerial combat forever. Are you ready to see how a humble spring could decide the fate of pilots in the deadliest skies? Let's dive in. War-torn Western Germany, February the 11th in the year 1945. A bitter winter day etched into history. At precisely 400 hours, a tense moment unfolded amidst the relentless chaos of aerial combat. Heinrich Roth, a seasoned pilot of Jagdgeschwader 26, gripped his control stick with a vice-like intensity, forcing it hard to the right at a blistering speed of 400 miles per hour. He could feel the fiery burn in his arm muscles as he fought to overcome the stubborn resistance of his aircraft's controls, which refused to yield even a millimeter despite his strenuous effort. The fighter he commanded was the formidable Focke-Wulf FW190, but now it was utterly uncooperative as its ailerons had become almost completely frozen at such a high velocity. Meanwhile, behind him, a Royal Air Force Hawker Tempest performed an effortless roll into a firing position, its four powerful 20mm cannons already tracking directly toward Roth's cockpit, ready to unleash destruction. The control stick in Roth's hand felt as though it had been welded in place, requiring over 60 pounds of force, something well beyond the normal, just to produce the slightest movement. In that moment, Roth's mind was perfectly clear, and he knew with absolute certainty that he was on the precipice of death. The ailerons, which should have given him some control, had effectively become immobile at this terrifying speed, leaving his aircraft vulnerable and uncontrollable. What made this peril even more tragic was the stark contrast in maneuverability displayed by the pursuing Tempest. The British fighter behind him moved as smoothly and readily as if each maneuver was happening at half the actual velocity. Such an ability defied the very laws of aerodynamics understood by the Luftwaffe's engineers. According to their well-authenticated theories and extensive testing, high-speed flight at such velocities, approaching 400 miles per hour, should have rendered even the most robust control surfaces ineffective, due to the immense aerodynamic pressures involved. Yet here was the Tempest, unfazed and fluid, effortlessly aligning its guns on Roth's doomed aircraft. Within mere seconds, maybe 3, the brutal barrage of 20mm shells tore into Roth's canopy, shattering it into jagged fragments. As the remnants of the canopy disintegrated and Roth's aircraft spiraled uncontrollably downward through the gray German sky, he became yet another tragic casualty in a technological revolution that the brightest minds within the Wehrmacht's engineering corps had scarcely understood or anticipated. The sinister efficiency of this revolution lay in a simple yet revolutionary device, the spring tab. This seemingly humble addition to the aileron mechanism transformed the Tempest into a formidable adversary that defied all the established assumptions about high-speed aerial combat held by German pilots. By February of that year, the spring tab aileron system was wreaking havoc among the Luftwaffe's top pilots, claiming lives at an alarming rate. During the month of January alone, an astonishing total of 47 Luftwaffe pilots lost their lives in encounters with Tempests. The reason was starkly clear. Many of these pilots discovered too late that, at speeds exceeding 350 miles per hour, their aircraft became nearly uncontrollable. The maneuverability of the British fighter, maintaining precise, effortless control, stood in stark contrast to the German fighters, like the Messerschmitt Bf 109 and the Focke-Wulf FW190, which struggled to sustain effective control under such extreme conditions. This disparity transformed what should have been a test of pilot skill into a brutal execution, where slow, careful maneuvering was replaced by a frantic fight for survival against a machine that shrugged off everything German engineers had known about aircraft control. The origins of Germany's disastrous disadvantage in controlling fighters at high speed traced back much earlier, in the summer of 1944. Reports first emerged at Luftwaffe headquarters about a new British fighter that seemed to challenge the fundamental principles of aerodynamics. These reports spoke of an aircraft capable of maintaining full aileron control, meaning the ability to roll, yaw, and pitch at speeds where the models of the time, the Messerschmitt Bf 109 and the Focke-Wulf FW190, experienced control forces so severe that pilots were physically unable to move their sticks even an inch. The forces exerted on their control sticks at such high velocities were so formidable that typical control surfaces, which depended primarily on aerodynamic pressures, were rendered practically useless unless supplemented by hydraulic assistance. But integrating hydraulics added considerable weight and complexity, making the fighters less agile and more vulnerable, an option that the German engineers naturally sought to avoid. Major Wilhelm Steinmann, commanding two groups of Jagdgeschwader 26, dismissed these initial reports as mere exaggeration or perhaps the result of pilot error. He confidently asserted that no aircraft could maintain effective control at 400 miles per hour without hydraulic help, because the aerodynamic pressures at such speeds made large control surface movements physically impossible. Any attempt to def a notable degree of physical effort from the pilot had they been flying a traditional unassisted control surface. This innovative feature effectively transformed the handling characteristics of the Tempest, enabling British pilots to maneuver with a level of agility typically associated with lower-speed aircraft, even when flying at the blistering velocities characteristic of combat situations. Unlike traditional fighters that saw their control responsiveness diminish rapidly as speed increased, the Tempest's spring tab system ensured that pilot input translated into precise, manageable movements, drastically reducing fatigue and enhancing combat effectiveness. The underlying principle of this system was elegantly straightforward yet profoundly effective. Each aileron was equipped with a small auxiliary surface called a spring tab. This tab was linked to the main control system via a finely calibrated spring designed to respond proportionally to aerodynamic forces. As the aircraft's speed climbed and aerodynamic loads on the controls intensified, the spring would compress accordingly, resulting in the tab deflecting in a direction opposite to that of the pilot's input. This deflection created an aerodynamic force, an assist, that effectively eased the movement of the main control surface, ensuring that even at high velocities, the pilot could alter the aircraft's attitude with minimal exertion. The genius of the spring tab system lay in its automatic and adaptive response. When flying at lower speeds, the aerodynamic forces were minimal, and the spring remained relatively relaxed, allowing the pilot to have full, direct control. However, at higher speeds, as aerodynamic forces increased exponentially, the spring compressed more, causing the tabs to deflect further and generate increased aerodynamic assistance. This process automatically compensated for the control heaviness that had previously hampered German fighter pilots, who had to exert extraordinary effort to maneuver once their aircraft reached combat speeds. The impact of this technological breakthrough was profound and multifaceted. It allowed the British to maintain superior control authority across a much broader speed spectrum, giving their fighters a decisive edge in dogfights and tactical engagements at high velocities. Pilots flying the Tempest could execute rapid roll, pitch, and yaw maneuvers with a degree of responsiveness that was previously believed unattainable without hydraulic or power-assisted systems. This enhancement not only improved tactical agility, but also reduced pilot fatigue during extended combat operations, thereby contributing directly to mission success and pilot survivability. The introduction of the Tempest's spring tab system marked a significant departure from the long-standing technical limitations afflicting high-speed fighters of the era. Prior to its deployment, much of the German engineering consensus had accepted the heaviness of controls at high speeds as an immutable consequence of the basic physics governing aerodynamics. The prevailing belief was that the increasing aerodynamic forces on control surfaces would always require substantial physical effort, and thus heavy controls were viewed as an unavoidable feature of high-performance fighters, an issue that, it was assumed, affected all combatants equally. This conventional wisdom persisted despite mounting frustration and mounting evidence that alternatives might exist. German engineers had experimented with small auxiliary surfaces, such as the Flettner tabs, fitted on some versions of the BF109G, hoping to alleviate the control heaviness without resorting to hydraulic assistance. These devices modestly reduced control forces, but provided only marginal improvement and were rarely adopted widely, leaving the majority of Luftwaffe pilots dependent on brute physical strength and stringent speed management to maintain control at high velocities. It was this deeply ingrained assumption that the Germans believed to be insurmountable, that heavier controls at greater speeds were an inherent consequence of aerodynamics, leading to a kind of defensive technological stagnation. However, the arrival of the Hawker Tempest and its revolutionary control system in April of 1944 shattered this misconception entirely. Unlike previous mechanical approaches, the Tempest's spring tab system provided a passive, automatic solution that dynamically adapted to the aircraft's speed, offering an elegant feather in Britain's already impressive technological cap. The significance of this development extended beyond mere mechanical ingenuity because it represented a paradigm shift in high-speed aircraft control philosophy. The British demonstrated that it was possible to engineer control systems that retained their responsiveness across a broad spectrum of speeds, thus revolutionizing fighter aircraft design. The Tempest's success in this regard proved that the perceived physical limitations were not insurmountable laws of nature, but rather challenges that could be mitigated or even eliminated through novel engineering solutions. Test pilots like Eric Brown, a renowned British aviator who would later evaluate captured enemy aircraft, often remarked on the remarkably intuitive control feel of the Tempest at high speeds. During his initial flights in the aircraft, Brown observed that the roll rates and overall maneuverability appeared almost unnatural, as though the aircraft had been decoupled from the typical forces that hampered traditional fighters. This sensation was a direct consequence of the spring tab's automatic assistance, which maintained a consistent, manageable control pressure regardless of velocity. In essence, the Tempest's innovative control system ushered in a new era in aircraft controls, highlighting how clever engineering could overcome what once seemed like immutable physical barriers. Its success not only improved British combat tactics, but also challenged the assumptions of all aeronautical engineers regarding control force limitations at high speeds. Imagine a sensation akin to harnessing a force that felt almost supernatural, superhuman strength, when piloting certain advanced fighters, a feeling comparable to the power steering of classic automobiles before such systems even existed. This extraordinary control allowed pilots to make precise, seemingly effortless inputs at astonishing velocities, where ordinary aircraft would become uncontrollable and twitchy. Yet these specialized fighters responded with remarkable smoothness and agility. Essentially, this system granted pilots the ability to maneuver with a finesse that bordered on the impossible, even at speeds that would normally turn aircraft into unwieldy, nearly uncontrollable machines. This remarkable technology did not appear overnight. It was the culmination of meticulous engineering efforts, carefully tested and refined over many months. Engineers at the Royal Aircraft Establishment at Farnborough conducted extensive wind tunnel experiments, meticulously studying the aerodynamic properties and control responses of these fighters. Simultaneously, Hawker's engineers, based at their facility in Langley, dedicated themselves to perfecting the design elements, such as spring rates and tab geometries, necessary to generate the ideal force reduction in control surfaces. These adjustments aim to achieve a delicate balance, reducing the pilot's effort required to manipulate the controls without provoking flutter or other aeroelastic issues that, under high-speed conditions, could lead to catastrophic structural failure of the aircraft. The presence of this unique system first became evident to enemy pilots during the campaign in Normandy, where the British Tempest fighters started appearing increasingly over the battlefield. With time, reports from combat missions began describing a series of astonishing maneuvers performed by these aircraft, maneuvers that seemed almost impossible for others to match. British fighters could maintain aggressive rolling and turning movements at dive speeds that summoned the limits of physical control. Enemy observers noted that while German aircraft like the Focke-Wulf 190 and Messerschmitt Bf 109 struggled with control forces, especially at high velocities, the Tempest remained remarkably responsive and easy to handle. One of the most illustrative encounters occurred in September 1944 over Belgium, involving a seasoned German ace, Joseph Priller, who was flying his Focke-Wulf 190. During a high-speed dogfight, Priller recalled how his aircraft suddenly felt as if it had turned into a massive, immovable block of concrete once reaching speeds around 400 miles per hour, a velocity at which his plane's controls became stiff and unresponsive. Meanwhile, the British Tempest danced effortlessly through the air, executing a barrel roll that Priller later described as physically impossible for his own aircraft, an action that highlighted the disparity in control capabilities at those extreme speeds. This encounter was far from isolated. During the autumn of 1944, numerous combat reports painted a troubling picture for the Germans. Many pilots described being outmaneuvered by this new breed of aircraft, maneuvering at velocities where their own fighters felt sluggish and unresponsive, threatening to turn the skies into a domain where they could barely maintain controlled flight. The problem was especially acute for pilots flying the Bf 109. A fighter with a narrow cockpit that physically limited their ability to apply lateral stick forces, those required to bank or turn the aircraft effectively. Facing the high risks of high-speed dives to evade enemy fire, these pilots often found themselves entering steep dives in which their aircraft, hampered by control stiffness, became essentially a straight line in the sky. Meanwhile, the Tempest pilots maintained full maneuverability throughout these high-speed descents, effortlessly following their opponents down and keeping the advantage, thanks to their aircraft's enhanced control system. By November of 1944, this emergent threat had become so serious that it drew the immediate attention of high command. General Durjagdflieger Adolf Galland, recognizing the gravity of the situation, ordered a thorough technical investigation into the mysterious capabilities of the Tempest fighters. A team of engineers was assembled from noted companies such as Messerschmitt and Focke-Wulf. Their task was to analyze combat footage, examine wreckage from crash sites, and uncover the secret enabling British pilots to retain such control at speeds that rendered German fighters as immobile as flying bricks. The initial phase of this investigation was marked by a misdirection of effort. Engineers presumed that the British might have been using some sort of advanced hydraulic boost system or revolutionary aerodynamic design features, innovations that could enhance control at high speeds. However, they overlooked a simpler but equally effective solution: a mechanical device that had been visible in numerous crashed aircraft but was misunderstood or dismissed. This device was none other than a specialized trim tab, a small adjustable surface on the control surfaces, which, when fine-tuned correctly, could significantly reduce the force needed to operate the aircraft's controls during high-speed maneuvers. The breakthrough came in December 1944, when Luftwaffe's technical officers at the reclusive research facility in Reclan finally uncovered the truth. Upon examining a relatively intact wreck recovered from a recent combat, they realized that the secret to the Tempest's unparalleled control was rooted in a sophisticated yet straightforward mechanical solution. This revelation explained why British pilots could execute such precise and effortless maneuvers during a fierce confrontation near the Rain airfield. A storm of a different kind was unleashed, one that would ultimately change the course of aerial warfare. It was during this intense clash that a remarkable discovery was made, unveiling the true capabilities of a seemingly simple yet profoundly effective control mechanism, the spring tab system. This revelation came as a shock to the engineers and pilots alike, as it became increasingly clear that this modest mechanical device had the power to fundamentally transform aircraft handling at extreme speeds. At the outset, the engineers conducting a thorough examination of the wreckage were led by Dr. Friedrich Zimmermann, a prominent scientist affiliated with the Deutsche Versuchsanstalt für Luftfahrt, German Institute for Aviation Research. Their initial reaction was one of disbelief. The notion that such an uncomplicated mechanical system could yield such drastic improvements in pilot control and aircraft responsiveness seemed almost too good to be true. To validate their assumptions, they performed rapid calculations and tests which confirmed that the spring tab mechanism was capable of reducing the forces required to control the aircraft by as much as 70% when flying at maximum speeds. This was a considerable leap forward, offering pilots a much more manageable experience even under the most demanding flight conditions. Zimmermann's detailed report to the Air Ministry painted a stark picture of this technological breakthrough. He underscored that the enemy had already incorporated this advanced control system into their latest fighter aircraft, bestowing upon their pilots an unprecedented advantage. According to his findings, these fighters could sustain full combat maneuverability at velocities where our own aircraft would often become nearly uncontrollable. Zimmermann emphasized that the Germans had previously underestimated the potential of mechanical control systems, but this discovery demonstrated that simple mechanical solutions could yield advantages previously thought attainable only through complex electronics or refined aerodynamics. However, implementing a similar system into existing German fighters would not be straightforward. Zimmermann's report outlined that retrofitting the spring tab mechanism would demand extensive redesign and rigorous flight testing, processes that could span multiple months or even several years. Such delays posed a significant challenge to the German war effort, prompting urgent discussions among high-ranking officials. This revelation immediately sparked a crisis meeting at the headquarters of Luftwaffe, the German Air Force, where General Galland confronted Hermann Göring with the troubling truth. The British, and by extension the Allies, held a decisive technological edge that could not be swiftly neutralized. The identification of this advantage deepened the growing tension within the German leadership concerning the conduct and strategy of the air war. There was a palpable concern that without rapid adaptation, their fighters would fall behind in the relentless race of technological innovation. Meanwhile, in the broader context of the Axis alliance, similar shock waves rippled through Japan. Japanese and German military partners found themselves equally astonished when they observed American fighters equipped with advanced control systems. These fighters, particularly the P-51 Mustang and the P-47 Thunderbolt, demonstrated remarkable stability at high velocities, with pilots experiencing control reckoning that made their aircraft nearly unflinchable at speeds exceeding 300 miles per hour. Japanese Imperial Army Air Force pilots revealed that their manually controlled fighters, such as the Mitsubishi Zero, became increasingly difficult to maneuver as they approached these velocity thresholds. Despite their efforts to modify these aircraft with interconnected aileron flap systems or other mechanical aids, none could match the dramatic effectiveness of the British spring tab system. This left them vulnerable to the same well-documented high-speed control limitations that had already compromised their German allies' aircraft. The renowned Japanese ace Makoto Ogawa, credited with downing 7 B-29 bombers during the war, vividly described the combat experience in his post-war memoirs. He compared fighting American fighters at high speeds to engaging with one hand effectively tied behind his back. Ogawa observed that above 300 miles per hour, Japanese fighters like the Zero and others encountered control forces so daunting that aggressive maneuvers, essential for evading or engaging enemies, became physically impossible. This limitation significantly hampered their combat effectiveness at the speed range necessary for successful, high-altitude, high-speed dogfights. In Italy, efforts were underway to address similar issues with their own fighters, such as the Machi C-202 Falco and the later C-205 Veltro. Italian engineers experimented with various control system modifications, including interconnected aileron flaps designed to lessen the heavy control loads experienced at high velocities. These measures provided only incremental improvements and fell far short of the revolutionary impact of the British spring tab system. Consequently, Italian pilots faced the same perilous control challenges as their German and Japanese counterparts, especially during high-speed pursuits or evasive maneuvers at speeds surpassing 300 miles per hour. One of Italy's top aces, squadron leader Franco Lucini, constantly voiced his frustrations over the handling characteristics of the Machi fighters. In his combat reports and interviews, He remarked that these aircraft felt almost like wooden frames at high speeds, requiring Herculean physical effort from the pilot to execute even basic maneuvers during enemy engagements. The inability to perform aggressive or swift evasive actions in such the development and deployment of the Tempest V series, one aircraft represent a remarkable story of technological innovation, refined through relentless testing and practical application. After extensive flight testing, engineers and designers successively fine-tuned various components, particularly focusing on the spring tab system, and aerodynamic control assist designed to optimize maneuverability. Through these rigorous evaluations, they identified the ideal combination of spring rates and tab dimensions, balancing maximum effectiveness in control response with the imperative to maintain the structural integrity of the airframe. This meticulous process ensured that the aircraft delivered superior agility without risking undue stress or potential failure under demanding conditions. Initially, the first batch of 100 Tempest Defy Series I fighters incorporated this advanced spring tab control system. These aircraft demonstrated exceptional agility, but as their operational use expanded, some were temporarily withdrawn from combat roles towards the end of the year 1944. It was during this period that the true implications of their enhanced maneuverability became evident. Pilots pushing the aircraft to the limits at high speeds occasionally applied full control inputs. This aggressive handling occasionally led to overstressing the airframe because the increased forces on control surfaces surpassed the original design margins, revealing the need for structural reinforcement in some cases. These issues underscored the importance of providing pilots with additional training to adapt to the new handling characteristics, ensuring they could exploit the aircraft's capabilities safely and effectively. The origins of the spring tab solution can be traced back to the insightful observations of Sidney Cam, who served as Hawker's chief designer. Early in the development of the Tempest, Cam recognized the critical challenge posed by high-speed control forces, which threatened to limit the aircraft's performance potential. Drawing on his prior experience with the Hawker Typhoon, a fighter that had been plagued by excessively heavy controls, Cam understood the importance of reducing control forces to improve pilot endurance and combat effectiveness over extended engagements. Collaboration with aerodynamic specialists at the Royal Aircraft Establishment yielded innovative solutions, leading to the creation of the spring tab mechanism. Unlike more complex and heavier hydraulic systems, the spring tab offered a straightforward, reliable, and lightweight method for augmenting control surfaces, making it a suitable choice for high-performance fighters. Manufacturing the spring tab-equipped ailerons involved a level of precision that was, at the time, quite extraordinary. Each aircraft's control system required individually calibrated springs, with tolerances measured in thousandths of an inch, an incredibly exacting standard. This painstaking process entailed meticulous testing of each aileron assembly to verify that the tabs responded correctly over a range of speeds and maneuvers, ensuring that pilots could depend on consistent control forces in combat. Achieving such a high standard of quality control was formidable, particularly considering the increasingly strained conditions in German industrial facilities by 1944, which hampered their ability to produce comparable precision components. At Hawker's factory in Langley, skilled workers, many of whom were women called upon to fill roles left vacant by men called into military service, assembled these sophisticated mechanisms. Their work demanded extraordinary attention to detail, with measurements accurate to within a fraction of a thousandth of an inch. These artisans understood that their precision work directly impacted pilot safety and combat survivability, especially as pilots operated at speeds approaching 400 miles per hour. The effectiveness of this technological innovation was vividly demonstrated between December 1944 and February 1945, when Tempest squadrons achieved astonishing results. During this period, they claimed the destruction of approximately 239 German aircraft, suffering only the loss of about 20 Tempests in return. This translated into a highly impressive kill ratio of roughly 7-to-1, a statistic that reflected not only pilot skill, but also the vital advantage conferred by the improved control system at speeds where enemy fighters were rendered nearly helpless. A notable testament to the Tempest dominance was conveyed by squadron leader David Fairbanks, the fighter's highest-scoring ace. He recounted numerous encounters where German fighters attempted swift escape by diving at high speed. However, these pilots found themselves trapped because their aircraft could not match the maneuverability of the Tempest. Fairbanks's Tempest could perform aggressive, tight turns and sustained high-G maneuvers, while their enemies, limited by their own aircraft's control constraints, were forced into straight-line dives. This tactical advantage turned what should have been successful evasive actions into near-suicidal opportunities, giving the Tempest pilots a decisive edge in dogfights. The psychological impact of this technological superiority on the Luftwaffe's pilots was profound and deeply damaging. They quickly realized that their aircraft had an inherent disadvantage in maneuverability at high speeds, a flaw that no amount of skill, training, or bravery could fully negate. This realization eroded confidence among Luftwaffe fighter crews, sowing panic and frustration as they faced a foe that could outmaneuver them, even under stressful combat conditions. This crisis of morale spread through fighter units, creating a tangible sense of vulnerability and vulnerability, shaking the confidence of many seasoned pilots who once believed in their aircraft's capabilities. The decisive advantages offered by the spring tab system and the overall aerodynamic. The combat experience of Bulligan of Jagasheer II, a seasoned fighter pilot with over 100 combat missions behind him, offers a vivid illustration of the technological disparities that defined aerial warfare during the final years of World War II. In a heartfelt letter penned in January of 1945 to his wife, Bulligan described a bleak reality. Despite their relentless efforts, they were fighting with weapons and technology that had seen their prime days long ago. His words vividly conveyed a sense of helplessness as he watched enemy Tempests, those advanced Allied fighters, maneuver effortlessly through the sky at speeds that rendered his own FW190, the famed 190D series, sluggish and nearly cumbersome, akin to a heavily loaded bomber struggling against the wind. To Bulligan, the stark contrast painted a picture of a battle being fought not just with guns and layers of metal, but with the persistent shadow of technological obsolescence looming large over their efforts. During this period, the German aviation industry endeavored with great urgency to catch up, applying what limited resources and knowledge they could muster. However, their attempts to field faster, more capable fighters akin to the Tempest faced formidable obstacles. The industry was grappling with severe shortages of vital materials that hampered mass production, leading to delays and reduced output. Moreover, the dispersion of factories, an unfortunate consequence of relentless aerial bombing campaigns, halved their logistical capacity, while the loss of experienced engineers either to military service or to captivity by Allied forces further crippled their developmental programs. The complex process of redesigning aircraft with new control systems or modifications, including the much-anticipated spring tab device, required extensive testing. These constraints made rapid deployment or refinement of such innovations practically impossible during this desperate phase of the war, leaving pilots to contend with increasingly outdated equipment. In an emergency effort to improve aircraft controllability, some FW190D13 models were hastily fitted with hydraulic aileron boosting systems. Only a small batch of these aircraft ever saw service before the war's end, however, as the addition of hydraulic controls brought with it undesirable weight penalties and increased mechanical complexity. These modifications often degraded aircraft performance in other flight regimes, such as low or medium speeds, thus serving as imperfect substitutes for the elegant and efficient spring tab solutions that had been conceived but not widely implemented. Spring tabs, which essentially reduced pilot workload by simplifying control inputs during high-speed maneuvers, remained a promising but largely unrealized technological leap for the German fighters, hampered by wartime limitations. The Luftwaffe's fighter force, already battered by fuel shortages, inexperienced pilots, and meager numbers, found itself further weakened by the inability to innovate effectively in aircraft control systems. The technological gap became yet another factor accelerating their decline. As their pilots increasingly became aware of their aircraft's limitations at extreme speeds, they consciously avoided high-velocity dogfights where they knew the risks of losing control or being overwhelmed were significantly higher. One notable example of this change in tactics was the Boden-Platte operation on the 1st of January of 1945, when the Luftwaffe launched a massive surprise attack against Allied airfields. This raid was driven in part by the desperate need to eliminate enemy fighters on the ground before they could engage German aircraft in the air, especially considering that engaging in high-speed aerial combat had become a near-suicidal endeavor against opponents like the Tempest, which possessed superior aeronautical control capabilities. The advantages conferred by the spring-tab design extended well beyond raw combat effectiveness. Tempest pilots could adopt more aggressive pursuit tactics, pressing their advantage without the exhaustion that normally sapped the strength of fighter pilots flying conventional aircraft. The reduction in control forces required to pilot these aircraft meant that pilots could sustain longer missions with less physical fatigue, thereby maintaining peak operational performance throughout extended engagements. This meant that, unlike their adversaries, Tempest pilots were capable of high-intensity combat over prolonged periods, undeterred by the physical toll of controlling their aircraft at high speeds. Flight Lieutenant Pierre Clustermanman, serving with 274 Squadron, vividly described the difference after his transition from flying Spitfires to Tempests. He observed that with the newer fighters equipped with spring tabs, he was able to fly twice as long without succumbing to arm or shoulder fatigue that had previously limited his ability to sustain prolonged dogfights. The spring tabs transformed control inputs into a sensation akin to moving calmly through the air, rather than struggling against a sluggish, resistive force at combat speeds. This seemingly small technological enhancement had a profound impact on pilot endurance and combat effectiveness, enabling pilots to maintain their focus and agility longer in the heat of battle. Post-war technical assessments, carried out at a remote American research facility where captured German fighters were extensively tested, confirmed the significant control issues that had hindered the Luftwaffe's aircraft. American test pilots, who examined the fighters in detail, expressed amazement that German pilots had managed any success at all, given the severe control force limitations of their aircraft at high velocities. These evaluations revealed that, despite the FW190's excellent handling at low, the experience of high-speed aircraft handling during the Second World War revealed a persistent and critical issue. Many fighters, despite their impressive speed and firepower, suffered from inadequate or poorly designed control systems, which severely compromised pilot effectiveness and safety. For example, the German Messerschmitt B F109G, a prominent fighter of the era, was notably hampered by its narrow cockpit, a design feature that profoundly impacted pilot performance. This constricted environment made it physically impossible for most pilots to exert enough lateral force on the control stick to achieve full aileron deflection. As a result, even when flying at high speeds where precise maneuvering is essential, pilots face substantial difficulties in executing effective rolls and turns, limiting their aircraft's responsiveness and combat agility. The Battle of Britain and subsequent aerial studies underscored this problem, but perhaps the most incisive critique came from Captain Eric Brown of the Royal Navy. Brown, one of the most experienced and respected test pilots of his time, had the unique vantage point of extensively evaluating both German and British fighters. His assessments cut to the core of control system deficiencies. Brown pointed out that the FW190 fighter, despite its formidable reputation, suffered from a lack of spring-loaded control aids, such as spring tabs, that could have alleviated pilot workload during demanding high-speed maneuvers. Without these devices, the aircraft's controls at maximum speeds were essentially ineffective. Pilots might have as well been flying without ailerons at all, given their inability to generate sufficient lateral forces to fully deflect the ailerons and execute quick, precise rolls. In stark contrast, Brown observed that the British Hawker Tempest maintained a consistent level of responsiveness across its entire speed range. Its control system, he described, was akin to the difference between wielding a weapon and wielding a tool, a tangible metaphor for the aircraft's usability and responsiveness. The Tempest controls allowed pilots to maneuver effectively, whether flying at moderate or high speeds, providing a vital edge in combat situations that demanded rapid, accurate responses. Brown's evaluation of the BF109G was even more scathing. He identified the deadly combination of a narrow cockpit and heavy, stiff controls as a potential death trap during high-speed dogfights. The physical demands placed on pilots in such scenarios were immense. Despite their skill, they could not generate enough lateral force to control the aircraft swiftly enough. rendering their maneuvers sluggish and predictable. This limitation severely diminished combat effectiveness and increased pilot fatigue and danger. His observations highlighted the dire consequences of neglecting proper control augmentation in fighter design. Meanwhile, Italy's post-war analysis of captured Allied aircraft painted a similar picture of the superiority of advanced control systems. Italian Regia Aeronautica test pilots, after Italy's surrender, marveled at the technological edge of aircraft like the Tempest. Flying a captured Hurricane or Spitfire after operating Macchi fighters was compared to switching from a heavy truck to a high-performance race car, alluding to the remarkable ease with which these aircraft could be maneuvered at high speeds. The Italian pilots emphasized how the difference in control effort was stark, especially at those critical moments when maximum physical and mental effort was needed to keep the aircraft under control. Particularly striking was the testimony of Major Adriano Visconti, one of Italy's most accomplished fighter aces. In early 1945, Visconti flew a captured Tempest and reported that if Italian fighters had been equipped with similar control assistance technology, like spring tabs, they would have experienced a radical improvement in their combat capabilities. He believed that such innovations might have decisively altered the balance of aerial power over the Mediterranean, giving Italian pilots a fighting chance to compete against the Allies' more advanced fighters. The Japanese approach to aircraft design, despite their well-earned reputation for ingenuity, did not adequately address the challenge of high-speed control. Their focus on creating lightweight, highly maneuverable fighters meant sacrificing some pilot assist features that could have made high-speed handling more manageable. Consequently, Japanese fighters during the war became essentially helpless at high speeds against American aircraft equipped with enhanced control systems. Many Japanese pilots post-war expressed confusion about how American fighters consistently outperformed their own in high-speed dogfights. They believed that superior pilot training or mysterious technological advantages were the primary reasons, failing to recognize the fundamental role of control systems like spring tabs that preserve maneuverability across the aircraft's entire speed envelope. Meanwhile, Soviet engineers, tasked with examining captured German fighters and evaluating available intelligence from the Allies, including materials received through Lend-Lease agreements, quickly grasped the significance of control force reduction technologies. They recognized that to improve Soviet aircraft performance at high speeds, reducing pilot effort through cleverly designed control systems was essential. Early Soviet efforts, however, faced challenges achieving the elegant simplicity and effectiveness exemplified by British spring tab systems. Led by the prominent aircraft designer Alexander Yakovlev himself, the Soviet Design Bureau dedicated considerable effort to solving this complex problem. Yakovlev noted that the spring tab represented a straightforward yet profoundly effective solution to a complicated issue. It was, in the post-war period, as the French aviation industry embarked on an arduous process of reconstruction, it gained access to a wealth of technological insights from both German engineers and Allied sources. This combination of knowledge fueled extensive research in aircraft control systems, with engineers at the Société Nationale de Construction Aéronautique et de Mécanique Aérospatiale, SNKCMA, dedicating themselves to understanding and improving flight mechanics. Through meticulous studies, they identified certain innovations that had been largely underestimated at the time, but proved to be game-changing in aerial combat. Among these, the implementation of the spring tab mechanism in aircraft control surfaces emerged as one of the most crucial, yet underappreciated technological advances of the war. This small but sophisticated mechanical device, the spring tab, offered pilots enhanced maneuverability and control authority, providing a decisive edge in high-speed dogfights. The significance of this innovation lay in its ability to reduce pilot effort while increasing responsiveness during rapid, complex maneuvers, a factor that often turned the tide of aerial battles without most involved combatants fully grasping why their aircraft performed so effectively. The spring tab's role in shaping the outcome of numerous engagements was subtle, yet profound, acting as a hidden advantage that could tilt the battle in favor of the aircraft equipped with it. One influential advocate of incorporating advanced control aids into aircraft design was Marcel Dassault, a visionary engineer whose company would later become one of Europe's premier manufacturers of fighter aircraft. Observing the catastrophic failures of Axis fighters during the war, Dassault was convinced that all subsequent aircraft designs must deploy the most sophisticated flight control enhancements. He witnessed firsthand how the limitations of control forces could severely hinder fighter performance and lead to disaster. His relentless push for innovation resulted in a focused effort to integrate spring tab technology across production models. By the war's end, production data painted a stark picture of the technological gap that had developed between the Allies and Axis powers. The British manufacturing effort, exemplified by Hawker, had produced approximately 1,722 Tempest fighters, many of which were equipped with spring-tab ailerons. This high-volume output showcased the Allies' commitment to deploying control system advancements at scale. Meanwhile, German attempts to retrofit their existing fighters with similar control system improvements yielded only a handful of aircraft before the collapse of the Reich. These efforts underscored the disparities not just in technology, but also in industrial capacity and strategic focus. At the Langley factory in particular, aircraft production of the Tempest surged to an impressive rate of 15 fighters per week by early 1945. Each of these fighters represented a significant escalation in aerial combat capability, a vital step toward establishing air superiority. The proliferation of Tempests with advanced control systems meant that the Allies could field fighters capable of dominating high-speed battles, maneuvers that had previously been challenging or impossible for older designs. Contrasting this progress, German industry lagged severely behind. Under relentless Allied bombing campaigns and persistent shortages of raw materials, German factories struggled to sustain even minimal levels of production. The human cost of this technological and industrial disparity was tragically steep. German fighter losses rose to unsustainable levels by early 1945, forcing the Luftwaffe to drastically reduce their engagement strategies. Pilots were increasingly instructed to avoid combat unless conditions were highly advantageous, essentially conceding air superiority to the Allies by default. The toll of these losses was staggering. In the month of January alone, when 47 German pilots lost their lives fighting Tempest fighters, the Luftwaffe suffered the equivalent attrition of an entire fighter group, an insurmountable blow to their operational strength. The situation was aggravated by the collapse of Germany's once robust pilot training programs, which could no longer produce pilots with adequate experience. Additionally, replacements arriving at the front lines had minimal flying hours and little combat preparation, further degrading the quality of German aerial forces. This deterioration in pilot proficiency and aircraft quality compounded the inability to effectively contend with the technological edge held by the Allies. The psychological impact of the spring tab advantage cannot be overstated. As word spread among Luftwaffe units about the remarkable maneuverability of the Tempest fighters, attributes often described as nearly supernatural, an atmosphere of fear and despondency took hold. The concept of a phantom advantage began to haunt German pilots who, even before engaging in combat, perceived their chances of victory as slim. The whispered stories of Tempest pilots executing flawless, breathtaking maneuvers seemed almost supernatural, sowing seeds of doubt that seeped into the confidence of German pilots. This growing sense of helplessness contributed to a decline in aggressive tactics and increased caution, as pilots understood that confronting a Tempest at high speed was virtually tantamount to surrendering. In tactical terms, these perceptions created a damaging feedback loop. German fighters, previously confident and aggressive, started fighting from positions of disadvantage, often in defensive postures. The impact extended beyond morale. It translated into actual battlefield outcomes. The Luftwaffe was forced into a reactive stance, avoiding high-risk engagements and desperately trying to minimize losses, which further entrenched Allied air. The spring tab control system demonstrated notable advantages in terms of maintenance and reliability when compared to the more complex hydraulic alternatives. Its mechanical nature meant that it required minimal upkeep, rarely failing even after extended periods of use. In contrast, hydraulic systems, with their intricate networks of tubing, pumps, and actuators, introduced additional layers of complexity, weight, and potential points of failure. Such vulnerabilities could become dangerous in critical moments, especially when pilots depended heavily on their aircraft's control surfaces for successful maneuvers. Moreover, at forward airfields and frontline environments where resources and spare parts were often scarce, ground crews could maintain and fine-tune spring tab mechanisms with basic hand tools, making them a practical and dependable choice. Conversely, hydraulic systems needed specialized equipment and trained personnel for maintenance, a logistical burden that grew heavier as the war depleted supply chains and strained available expertise. The aerodynamic design of the spring tab system also warrants special mention. These small, precisely positioned tabs contributed very little to aerodynamic drag, yet they delivered maximum control enhancement. Unlike larger balance tabs or other mechanical aids, which could significantly increase drag and negatively impact aircraft performance, the diminutive spring tabs offered a clean solution. In fighter aircraft, where even a slight reduction in speed could determine survival, every increment of aerodynamic efficiency was crucial. Through meticulous wind tunnel testing at Farnborough, engineers optimized the size and placement of the spring tabs, ensuring they delivered the greatest control force reduction while imposing the least possible drag. This level of aerodynamic refinement was achieved despite the intense pressures and resource constraints faced by German engineers under wartime conditions. They could not match the British engineers' precision or practicality, which produced a control solution that balanced simplicity, effectiveness, and minimal performance compromise. The influence of the spring tab system extended beyond mere control efficiency into pilot training and operational flexibility. Because it required less physical strength to manipulate effectively, pilots could fly the Tempest more comfortably and with less fatigue. This meant that older pilots or smaller-framed aviators, who might otherwise have been physically unable to manage aggressive maneuvers, could remain combat-ready for longer periods. Such inclusivity broadened the pool of potential pilots and helped to lower training failure rates. This benefit grew even more critical as the war prolonged and experienced pilots became increasingly scarce. While the Luftwaffe aircraft suffered from control issues due to pilots lacking the physical strength necessary to handle high-speed maneuvers, the spring tab technology exemplified British pragmatic engineering at its best. It addressed a vital operational need with a solution that was both elegant in its simplicity and effective in its application. This approach starkly contrasted with German engineering philosophies, which often favored complicated and intricate solutions that, while innovative, frequently proved unreliable or difficult to produce in wartime conditions. German engineers pursued hydraulic control systems, variable geometry wings, and other advanced but complex mechanisms, all of which demanded heavy maintenance, specialized parts, and extensive production resources. British engineers, on the other hand, succeeded in creating a superior control system using just springs and tiny metal tabs, elements that were simpler, cheaper, and more resilient. This fundamental divergence in engineering philosophy had significant implications during the war, as practicality and reliability often proved more decisive than technological sophistication. Post-war assessments by the United States Strategic Bombing Survey underscored the broader significance of technological advantages like the spring tab system. These innovations were not merely tactical upgrades, they contributed to a cumulative decline in enemy morale and technological standing. The report highlighted how the Germans had assumed a parity with Allied technology, believing their systems were as advanced, only to discover that their assumptions were mistaken. German pilots and engineers thought they could match Allied aircraft's performance and control capabilities, but the reality was far more complex. When deficiencies in control systems became apparent, it affected pilot confidence, increased operational risks, and highlighted the technological gap that was widening as the war advanced. Such insights demonstrated that even relatively small technological improvements could ripple outward, influencing morale, operational effectiveness, and ultimately the outcome of the conflict. In summary, the adoption of the spring tab control system exemplified a strategic triumph of practical engineering over unnecessary complexity. Its reliability, aerodynamic efficiency, and the ease with which it could be maintained or adapted made it a vital component of British aircraft design during the conflict. The system's simplicity and ingenuity reflected a broader wartime philosophy, favoring solutions that were effective, resilient, and straightforward, rather than the elaborate and often fragile mechanisms favored by other nations. The technological edge provided by innovations like the spring tab was critical in maintaining the operational effectiveness of Allied aircraft, contributing in subtle but meaningful ways to the eventual Allied victory and the shifting balance of technological power in the skies. The development of the spring tab system proved to be a groundbreaking advancement, especially in terms of its impact on pilot confidence and aircraft maneuverability. This innovative control surface mechanism subtly but effectively transformed the way high-speed aircraft responded to pilot inputs. Unlike traditional control systems, which relied solely on the pilot's manual effort to move the control surfaces, spring tabs introduced a preloading feature that made maneuvering at high velocities more responsive and less physically demanding for pilots. It became particularly effective in combat situations, where rapid and precise control could mean the difference between victory and defeat. This technological breakthrough not only shook the perception of German engineering superiority during the wartime period, but also laid the foundation for the evolution of modern flight control systems. The influence of the spring tab concept persisted well beyond the Second World Conflict, as various iterations of the technology continued to be integrated into aviation design, serving both military and civilian aircraft for many decades thereafter. The simple elegance of the spring tab, devised under intense wartime pressure, demonstrated that fundamental aerodynamic concepts could be refined and adapted into robust, reliable systems with lasting impact. Indeed, the core idea behind spring tabs has become an essential element in contemporary fly-by-wire systems. These sophisticated controls, which provide artificial feel to the pilot and allow for automatic adjustments of control forces, can trace their conceptual heritage back to the humble but highly effective spring tabs that first granted Tempest pilots a significant tactical advantage. Such continuity shows how wartime innovation often leads to technological advances that shape the future, transforming basic mechanical principles into the complex electronic systems we rely on in modern aviation. However, the story of the spring tab also serves as a cautionary tale about the dangers of complacency and overconfidence in technological assumptions. German engineers, convinced that controlling high-speed aircraft was impossible without elaborate hydraulic systems, failed to recognize simpler control solutions that had already been successfully implemented by their rivals. This blind spot in their understanding meant they overlooked a crucial opportunity, an oversight that proved costly in the brutal realities of aerial combat. Their inability to develop or adopt the spring tab system early on deprived their pilots of a vital advantage, resulting in tragic losses and reduced effectiveness at critical moments. Historically, this neglect played a role in the Luftwaffe's diminished capacity to challenge Allied air supremacy during the final months of the war. The consequences of a single overlooked innovation underscored how strategic advantage could hinge on relatively simple technological insights. Personal accounts from German pilots who experienced encounters with Tempest fighters vividly illustrate this point. These accounts describe moments of paralysis and helplessness at high speeds, scenarios where pilots found themselves unable to maneuver effectively while enemy fighters maintained total control. Such situations transform what should have been an advantage, like diving at high speed into a perilous trap, often leading directly to disaster. One notable survivor's testimony, that of Officer Wilhelm Hoffmann, who was shot down by a Tempest in February of the year 1945, vividly conveyed the terror of this helplessness. Hoffmann described the experience as akin to paralysis. He felt immobilized as if struck by a powerful force, while the Tempest behind him moved gracefully, almost as if dancing through the sky. His aircraft, a BF-109G, had become unresponsive at roughly 400 miles per hour, while the enemy aircraft exhibited a level of control and agility that seemed almost to defy physics. The archaeological study of the Hawker-Langley manufacturing plant, even though much of it was destroyed or obscured by post-war development, revealed compelling evidence of the meticulous craftsmanship required for the production of the spring tabs. Workers' memoirs recall a rigorous emphasis on quality control, with management insisting that even a tenth of an inch variance in component dimensions could mean the difference between life and death for a pilot. This meticulous attention to detail underscored the recognition that the spring tabs were not merely small mechanical parts, but critical safety devices that could decisively influence the outcome of aerial combat. During the war, the sensitive and classified nature of springtab technology meant that many Allied pilots were unaware of the true significance of these components. Squadron intelligence officers were instructed to describe the system in vague terms if captured in order to protect the secret, an indication of just how crucial and strategically valuable this innovation was. Even among the Allies, understanding of the springtab's true capabilities remained limited, underscoring a strategic advantage kept well concealed from adversaries. Despite extensive efforts by German intelligence agencies to acquire detailed information on Allied aircraft technology, they ultimately failed to fully comprehend or appreciate the importance of the springtab system. Their inability to decode this critical aspect of Allied aircraft control mechanisms represented a significant intelligence failure. Had they understood the full potential of the system, it might have altered the strategic dynamics of the aerial combat during the war's closing stages. This lack of insight exemplifies how a seemingly minor technological element can have profound strategic consequences, often hidden in plain sight, yet wielding enormous influence over the outcome of conflicts. In summary, the story of the springtab encapsulates the profound impact that innovative mechanical solutions can have. During the height of the conflict, a significant challenge emerged concerning the aircraft's control systems, which, when examined after crashes, revealed critical flaws that had gone undetected until it was too late to implement effective countermeasures. This deficiency in control technology did not merely manifest in immediate combat losses, it also cast a long shadow over the wider strategic and economic framework of the war effort. For example, the urgency of addressing the control system's inadequacies forced the Luftwaffe aircraft manufacturing and maintenance crews to divert vital resources toward developing emergency interception and mitigation solutions. Among these stopgap measures was the installation of hydraulic boost systems designed to ease pilot fatigue and improve maneuverability under combat conditions. However, these systems required considerable time, personnel, and financial expenditure, resources that could arguably have been better allocated toward increasing the production rate of aircraft or expanding pilot training programs. In essence, the hidden costs of the technological shortfalls were deeply embedded in the man-hours dedicated to investigating and attempting to counteract the so-called springtab advantage. These efforts represented an invisible drain on German resources during a period when every asset was immensely valuable to the Reich's strategic endurance and survival. It is only in the subsequent years, long after the war's conclusion, that these issues gained the recognition they deserved. Early post-war histories tended to emphasize more glamorous innovations like jet engines or radar technology, often framing these advancements as the pivotal turning points of aerial combat. The relatively modest mechanical device, a simple spring-loaded control tab that provided such decisive advantages in traditional fighter engagements, was frequently overlooked or underappreciated in the broader narrative of technological progress during the conflict era. Only with the benefit of more detailed technical analyses undertaken by aviation historians in recent decades has the true significance of the springtab system come into clearer focus. These in-depth studies have uncovered how a seemingly minor mechanical innovation could generate profound strategic implications, effectively altering the balance of aerial combat. The accounts from ground crews serving on Luftwaffe aircraft further illuminate this narrative, revealing a stark picture of how the control system crisis manifested in reality. Mechanics describe pilots returning from missions visibly exhausted, not only from the physical exertion of flying heavy controls, but sometimes overwhelmed to the point of being unable to fly again for days, due to muscular fatigue and strain. In contrast, pilots flying aircraft such as the Tempest could often complete multiple missions within a single day without suffering similar levels of fatigue. The chief mechanic Otto Bergmann of Jägerschwader Squadron 26 observed a rising number of pilot requests for modifications aimed at reducing control forces. These requests, born out of desperation, sometimes prompted dangerous field improvisations, such as removing armor plating or other structural components to shave weight, modifications that compromised aircraft integrity and increased safety risks. These measures underscored the severity of the disadvantage imposed by the flawed control systems and the willingness of crews to take dangerous shortcuts to maintain combat readiness. The story of the spring tab technology underscores an important lesson in innovation, the value of incremental development and continuous refinement. The control system fitted to the Tempest, for example, did not emerge overnight. It was the culmination of years of dedicated research, testing, and design improvements, stretching back to interwar experiments with aircraft control surfaces and systems. This progress exemplifies how investments in seemingly mundane or purely mechanical technology during peacetime could yield decisive benefits during wartime. Such advancements highlighted that sustained, persistent efforts to refine even modest innovations could have outsized strategic impacts when confronted with the pressures of combat. This broader perspective contrasts sharply with the approach historically employed by the Royal Aircraft Establishment, which adopted a systematic methodology characterized by extensive wind tunnel testing and rigorous theoretical analysis to identify and resolve control force problems. Their methodical process stood in stark contrast to the more spontaneous, ad hoc German engineering responses, which often failed to arrive at viable solutions until the crisis had already become acute. The divergence in approaches can be explained, at least in part, by cultural factors influencing technological development within the two nations. German engineers, heavily focused on demonstrating sophisticated, innovative solutions, tended to favor complexity and technical brilliance over simplicity and practicality. The tendency was to develop intricate, state-of-the-art systems that showcased engineering prowess, even if these solutions were less effective in practice. This cultural inclination may have contributed to their overlooking or underestimating simpler, more effective improvements, such as spring tabs, which required fewer resources and could be implemented more swiftly. Meanwhile, the German emphasis on revolutionary technological advances, such as jet propulsion and rocket technology, while responsible for some remarkable innovations, may have inadvertently blindfolded them to the value of evolutionary improvements like spring tabs. These incremental modifications could have delivered immediate, tangible benefits in pilot control and aircraft maneuverability, offering straightforward solutions to pressing operational problems. By prioritizing breakthroughs that promised dramatic headline-grabbing results, their focus often diverted attention from the steady yet crucial progress made through modest, iterative enhancements. In summary, this gap in perspective underscores a broader lesson about the importance of balancing revolutionary innovation with careful, incremental improvement, particularly in the context of military technology, the development and refinement of the control. The post-war adaptation of spring tab technology across a wide range of aircraft types vividly demonstrated its remarkable versatility and the robustness of the fundamental principle that Hawker aircraft had pioneered specifically for the Tempest fighter. This innovative aerodynamic control system was not confined solely to military aircraft, but found its way into civilian aviation as well, with the Douglas DC-6, a popular post-war airliner, being directly inspired by the control improvements initially devised for wartime fighters. Such an evolution vividly illustrated how military technological breakthroughs, often driven by the intense and urgent needs of war, could be repurposed to enhance commercial aircraft, thereby benefiting the broader aviation industry. Although the roots of this technology originated amidst the desperate air combat of 1944 and 1945, their significance and the innovative spirit behind them were frequently overlooked or underappreciated in the post-war recounting of aviation history. During the final phases of the war, Germany faced mounting pressure to slow the Allied aerial advance. This led to increasingly frantic and often desperate measures to counter the dominance of aircraft like the Tempest. German commanders issued restrictive orders that fighters should not engage unless they possessed decisive advantage in numbers or altitude, restrictions that further diminished the Luftwaffe's effectiveness and ultimately played into the hands of Allied air superiority. One of the most tragic aspects of this struggle was the deployment of Ramjer units. German pilots trained to engage in suicidal ramming attacks upon Allied bombers. These units emerged partly because conventional interception tactics had become nearly impossible when faced with Tempests possessing superior speed, agility, and control. The sheer human drama involved young German pilots many of whom had accumulated fewer than 50 hours of flight time before being thrown into combat, epitomizes the tragic desperation of wartime aviation. They were often sent into battle against aircraft with technological and control advantages they could neither comprehend nor counter, underscoring the grim reality of asymmetrical technological warfare. In a bid to prepare new pilots for these unprecedented control challenges, flying training schools endeavored to simulate the difficult handling conditions these pilots would encounter. Yet no amount of classroom instruction or simulation could fully prepare aviators for the physical and mental demands of controlling aircraft at such extraordinary speeds, where Tempests maintained full authority over their maneuverability. The inherent physical limitations of human pilots became glaringly evident. No training could replace the fundamental aerodynamic advantage that the spring-tab control system conferred upon the Tempest. The surviving documentation related to the development and deployment of the spring-tab system offers invaluable insights into wartime innovation processes. These records reveal how British engineers engaged in meticulous problem-solving and iterative design, carefully balancing the urgent need for effective solutions with the constraints of mass production and wartime logistics. The detailed correspondence between Hawker's design team and Royal Air Force operational squadrons reflects a continuous cycle of improvement driven by combat experience, in stark contrast to the isolated and often disconnected approach of German aircraft manufacturers, who were increasingly cut off from frontline feedback by deteriorating communication channels and hierarchical command structures. The crucial role played by test pilots, in particular individuals like Bill Humble and Philip Lucas, deserves special recognition. These men undertook hazardous test flights to push the new control system to its limits, methodically exploring the boundaries of aircraft maneuverability to determine optimal spring rates and tab configurations. Their efforts were not merely experimental, they were essential to ensuring the safety and combat effectiveness of the aircraft. Their detailed flight test reports, retained in archives, reveal a systematic and disciplined approach to tackling aircraft control problems, testing dozens of configurations before arriving at the finely tuned design that bestowed the Tempest with its decisive aerial advantages. Following the war, the innovative spring-tab technology did not remain confined to Britain. It spread internationally, with former wartime enemies and allies alike recognizing its value for improving aircraft control and handling characteristics. Countries with burgeoning aviation industries adopted and adapted the principle, further refining the technology for both military and civilian applications, ultimately leading to safer, more maneuverable aircraft in a variety of roles and environments. This widespread dissemination of spring-tab control systems after the conflict underscores a broader truth. Wartime innovation, born out of necessity, often yields technological advancements that can influence civil aviation and technological development for decades to come. The legacy of the Tempest control enhancements persisted well beyond the battlefield, manifesting in safer, more efficient aircraft designs and demonstrating how adversity often spurs ingenuity and progress in engineering. During the course of the conflict, enemies transitioned from adversaries to collaborators, sharing crucial technical information that illustrated how innovation in military aircraft could transcend national borders for the collective good. One notable example was the post-war contributions of German engineers, who had initially grappled with understanding the mechanics of spring tabs during wartime. After the cessation of hostilities, these same engineers played a significant role in refining and enhancing spring tab technology for civilian use. Their efforts demonstrated a remarkable capacity for former enemies to come together in peacetime, working collaboratively to push forward the boundaries of aviation technology for the benefit of all. To quantitatively verify the advantage conferred by the spring tab system, detailed statistical analyses of combat engagement records were conducted between the British Tempest fighters and German aircraft. These analyses provided concrete evidence that Tempests consistently achieved favorable exchange ratios, even when facing numerically superior adversaries. Particularly in high-speed aerial combat, where the effectiveness of the control system was most critical, the Tempest's superior handling capabilities allowed it to outperform heavily outnumbered German fighters, reaffirming the tactical value of advanced control surface technology. Fundamentally, the mathematics of aerial combat traditionally favored the side with greater numbers. An overwhelming force could typically outmaneuver a smaller opponent. However, this principle was challenged and ultimately overturned by technological superiority. A single Tempest, equipped with the advanced spring tab control system, could effectively engage and neutralize multiple German fighters that struggled to maneuver at the same high speeds. These fighters, hampered by less responsive control surfaces and inferior aircraft handling characteristics, found it exceedingly difficult to match the Tempest's agility. This technological edge thus became a decisive factor on the battlefield. The manufacturing of spring tabs, particularly the springs themselves, entailed strict metallurgical standards due to their critical role in aircraft control systems. These springs needed to retain consistently predictable characteristics across a wide range of temperatures and endure millions of compression cycles without degradation. The British industrial sector excelled in this area, providing advantages that German industry, strained by war-related resource constraints and factory damages, could not match. The complexity of producing reliable high-performance springs further underlined the technological gap, as Germany's access to the necessary raw materials and manufacturing capacity diminished over time, adversely impacting their ability to produce comparable control systems. Moreover, the superior metallurgical quality of the spring alloys was a key factor contributing to system reliability. As raw material supplies became scarce and factories faced destruction or operational setbacks, Germany found it increasingly difficult to produce the highly specialized steel alloys required for dependable springs. This shortage added another layer of technological disadvantage, crippling their ability to produce control surfaces with the same level of consistency and durability as those developed in Britain. Beyond their technical function, spring tab systems profoundly impacted pilot psychology and tactical doctrine. The knowledge that Tempest pilots could rely on superior high-speed maneuverability forced German fighters to avoid entire classes of tactical situations, thereby restricting their strategic options. This psychological advantage translated into a ceding of initiative among Allied forces, as the Germans were often compelled to adopt more conservative tactics, aware of the Tempest's ability to dominate in high-speed engagements. The loss of an essential German tactic, high-speed slashing attacks, reduced their offensive options and eliminated a key element of their combat repertoire. Instead of executing swift, decisive strikes, German pilots found themselves engaged in turning battles, a situation unfavorable when facing technologically advanced aircraft like the Tempests. These dogfights often placed the Germans at a disadvantage due to their numerical inferiority and limited fuel reserves, which further diminished their operational effectiveness. Documentation describing the spring tab technology, found in technical manuals and training materials, reveals the meticulous efforts made to communicate complex engineering principles to pilots and ground crews. These materials provided crucial insights into the system's capabilities and limitations, ensuring that personnel could effectively operate and troubleshoot the system without requiring extensive technical backgrounds. The use of simplified explanations alongside detailed diagrams demonstrated an impressive pedagogical approach, making sophisticated engineering concepts accessible to personnel from diverse technical disciplines. A comparative review of various control force reduction methods studied during the war highlights the spring tab as the optimal solution. It struck an exceptional balance among effectiveness, simplicity, reliability, and ease of manufacturing, factors that contributed significantly to its success. This combination of qualities explained why the spring tab system outperformed alternative control augmentation methods, ranging from basic aerodynamic balance tabs to more complex devices like servo tabs, which often proved too intricate or unreliable under wartime conditions. In the course of experimentation, German engineers explored a wide array of control surface devices, including aerodynamic balance tabs and other mechanisms, in a bid to enhance aircraft maneuverability. However, despite their efforts, none matched the refined balance of effectiveness, manufacturability, and robustness offered by the British spring tab technology. This persistent pursuit further underscored the importance of these innovations in shaping the outcomes of aerial combat during the conflict. The investigations into the use of RVO tabs in conjunction with hydraulic boost systems revealed a fascinating complexity. Although in theory multiple solutions existed for implementing such devices, Only the spring tab design managed to successfully merge all the essential characteristics necessary for effective deployment during wartime conditions. This particular solution stood out because it embodied a perfect balance of reliability, effectiveness, and ease of integration, which are critical factors in the high-stakes environment of military aviation. Extensive examinations of aircraft wreckage, recovered after crashes, provided additional evidence pointing to a concerning lapse in German technical intelligence efforts. These investigations confirmed that by late in the fall of 1944, German authorities had already become aware of the existence and basic nature of spring tabs, yet their understanding remained superficial at best. Despite possessing knowledge of these devices, the Germans failed to fully appreciate their significance or to develop suitable countermeasures swiftly enough to influence the broader course of the war. Moreover, intelligence reports circulated within German circles frequently mischaracterized these devices as merely modified trim tabs. Such descriptions reflected a fundamental misunderstanding of the true function and strategic importance of spring tabs. Instead of recognizing them as sophisticated aerodynamic control surfaces capable of improving aircraft handling and safety, they were viewed as simple modifications, an underestimation that hindered counteractive innovation. This critical gap in technical analysis, this failure to accurately interpret and grasp the full potential and implications of spring tabs, had tangible, costly consequences for the German Air Force, known as the Luftwaffe. The consequences of this oversight became particularly pronounced during the final months of 1944 and the beginning of 1945-45, when the Luftwaffe faced mounting losses and was increasingly unable to counter the Allied advancements. In essence, this misjudgment and the sluggish response associated with it represented a significant strategic failure, ultimately costing the Germans dearly in what proved to be the waning days of their technological and military dominance.